Alright, hey AP Chemistry. So this will be the first video that I kind of make for all of you, and this is an example of how we will use videos that I make in this class to kind of help you out. So I got a couple of questions, either even Friday or even just over this weekend, about mass spectroscopy or mass spectrums, and this is an example. This was from your pretest that you took in May, and you may need to know how to answer this for your quiz this week. We started trying to do this question, but I'm going to start it from scratch, and then so you get the idea of how a mass spectrum works or how mass spectroscopy works. Now, please make sure you do the mass spectroscopy POGL. It explains like how we read and what is used to get a mass spectrum. What you need to remember is the only type of charge that a mass spectrum gets is positive charge, and typically on the x-axis, it's supposed to be a mass to charge ratio. And we get that from the POGL. It explains, like, you know, it fragments the pieces, and then you get certain pieces at certain masses and so on and so forth. Now, for this question, I just want to read and go through how we can interpret and what we do with the percentages. So it says the mass spectrum of an average sample of a pure element is shown in the figure above. Which of the following is the identity of the element? Now, I was starting this question in class, but the way this works is on the y-axis we have percent abundance, and on the x-axis we have mass or a mass to charge ratio. What this means is if I throw 100 particles of an element into a machine, okay, a certain percentage of them weigh a certain amount. And why do I say that? Isotopes, which is happening in chapter 2, are elements that are of the same identity but different mass. So, for example, I could have carbon 12 or carbon 13. These are two different isotopes of the element carbon. They are the same element, they're both carbon, but one carbon has a mass of 12 and one carbon has a mass of 13. And percent abundance-wise, if you look on the periodic table, the average atomic mass of carbon is like 12.01. And what that tells you is, since its mass is so close to zero, it means most of my particles, if I have 100 particles of carbon, it means most of them have a mass of 12, and maybe some of them, maybe a lot less, have a mass of 13. And so the way that we figure out the mass on the periodic table is by using an average atomic mass. And we get that from these percent abundances. So here's an element here. An element, let's say we have 100 particles of them, 50% of them, or 50 of them, 50% have a mass of 90. If I want to zoom down, 10% of them have a mass of 91. 20% of them have a mass of 92. And then another 20% have a mass of 94. Or if I wanted to read this as though I had 100 particles. If I had 100 particles of this element, about 50 of them would weigh 90, about 10 of them would weigh 91, about 20 of them would weigh 92, and another 20 of them would weigh 94. That would be their masses. And then if I put all 100 particles on a balance, I would get an average mass, or a weighted average of all these different masses. And so the way that I would calculate the average mass, right, so the way that I would calculate, I'm going to call it average atomic mass. And that's the number that's read on the periodic table on PT. PT is the periodic table. Is I take these weighted averages. So it'll be 50% of 90. And I add it to 10% of 91. And I add it to 20% of 92. And I add that to 20% of 94. Okay? So basically what I'm saying is if I want to get the average atomic mass, I take the percentage abundance of that mass and multiply it times that mass, and I add them all together. So if I want to do this math, 50% of 90, and now notice I'm doing this without a calculator. And so this is a no calculator section. This is on the AP exam from 2017, so 2 years ago almost. If I want to do 50% of 90, that has a mass of 45. If I want to do 10% of 91, 10% of 91 is like, if you do anything 10%, it's like dividing by 10. So it's 9.1. 20% of 92. Matt Maraka mentioned in class that, you could do 20% by dividing by, you could do 10% and then do that twice. So 20%, I like to divide by 5. Or you could divide by 10 and then divide by 2. So I'm going to divide by 5, though. So 20% of 92, anytime you do 20%, I'm going to write that on the side. 10% is like dividing by 10. 20% is like dividing by 5. If I want to do 92 divided by 5, I could do it the long way here, right? I'm going to do old school 5 divided by 92. 5 into 9, just that once. Minus 5, I got 42. 5 into 42 is about 8, because 8 times 5 is 40. And then I'm left with 2. And then I bring that over. 5 into 0.2, 18.5. So 18.5. And then I add that to 20% of 94. Okay? And that's, again, like doing 20%. 20% is like dividing by 5. So 20% of 94, I could do old school way. 5 into 94. 5 into 9 once. Minus 5, 9 minus 5 is 4, and then bring down the 4. Again, we got 18, and then minus 40, all right? And so now I have 8, and it's about, how do I do, sorry, you can't even see that. Sorry, you can't see that. So I did 5 into 9 is 1, bring down the 5, I have 4 left over, bring down the 4. 5 into 44 is about 8, and that's 40. And I got 4.0. And so now if I want to do 5 into the 0.4 or whatever it is, that's probably going to be about 0.8. And so now I have 18.8. Okay, so I'm just doing the long division way. And now what I want to do is add up all of these masses. And you could do that any which way. I could just do 45, 9.1, 18.5, 18.8. And so on and so forth. And I'm not going to do this math here. I'm going to leave that up to you because this may be a future quiz question, hint, hint. But once I get all of these masses, if I add up all of these weighted averages of the masses, the overall mass that I get is the mass that will be on the periodic table. So once I get a mass here, it should match one of these elements, either element Y, ZR, NB, or TH. And so the way that I could check that is if I look on the periodic table and I say which mass matches which element, and that's going to be the element of this spectrum. There was another question that was on your summer homework that asked, if all of the following is true, which would best explain the spectrum? You need to understand that the mass spectrum gives you a mass to charge ratio and talks about isotopes. So there's no other type of content that is included in this question. So there are only positive charges with here, so nothing about negative. You can't talk about anything with electrons here. I mean, electrons are ejected, but you can't talk about any type of energies here. The only thing that really you should worry about is percent abundance or abundance of isotopes here. And then another thing is, notice how the highest line here is this mass of 90. What this is saying is that it looks like over all the different isotopes present, there's a 90 isotope, a 91, a 92, and a 94. Since 50% is the highest number, it must be the most abundant isotope. It is the highest number. So if you ever hear the expression most abundant isotope, it's talking about, I'm going to write that down, most abundant isotope. When it's talking about that, it's talking about the isotope with the highest percentage. And usually it's the one that kind of pushes the average atomic mass to being that mass. So my mass may be somewhere between 90 and maybe 92 or 94. The least abundant is the 10%, and I might not be close to 91 as a mass. All right, and so we'll see when I add up all these masses, what mass will that match? Okay, so that was kind of a crash course on reading and interpreting mass spectra. If you have any other questions or concerns, please feel free to ask in class. On the AP exam, you will definitely get questions that look similar to this.